Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Hi and welcome back to the Neil Ashton podcast. Today's episode is really setting the scene for what are going to be a couple of really interesting interviews and discussions with some world-leading experts on machine learning. What the next month's episodes are really going to be focusing on is this topic of AI for science, or how artificial intelligence, how machine learning can be used to solve scientific problems, in addition to the way that machine learning is now increasingly being used for generative AI, for these large language models that you can go in and you can ask questions, you can generate images, increasingly you can generate short clips. How, or is it possible for some of those to also solve some of the scientific problems like computational fluid dynamics, weather modeling, material design, drug discovery, etc.? And I just wanted to set the scene really. Today's going to be a bit of a shorter episode, and I wanted to maybe discuss some of the fundamentals in terms of why this is becoming interesting. And I'm going to talk through the lens of CFD, of computational fluid dynamics, such that hopefully the next few episodes, when you listen to them with some of these world-leading experts, you'll get a little bit of the context, because we may dive in straight away in those conversations. So I thought this one might be useful to really explain some of the high-level concepts. So the way I would say it is this. So let's look at computational fluid dynamics. Let's look at what the previous 9 episodes have essentially been about, which is, okay, I want to design a car or a plane or a wind turbine or a jet engine. And I could do it physically, as in, I could build it and fly it and test it. But most of the time that's too expensive, so people don't do it. That's really left right to the end. It's not really a development thing. Sorry, I think I've got a bit of a cold or something, so my voice is going a bit. What is increasingly used more are either wind tunnel tests, so some sort of artificial environment that mimics the real world, but let's say in a very large warehouse where you blow air over like an object, or you do some sort of lab test where you maybe have like a jet engine inside a building which is detached from a plane, and you do some experimental tests. But even those are arguably still quite slow and limit the number of designs you can explore, and hence why simulation is so widely done now, and hence why computational fluid dynamics is this important area that continues to grow in terms of its applicability. And that's why I constantly talk about CFD, because it really is used in so many of the things that you're used to doing. But if you're doing CFD, and this applies also to, let's say, drug discovery or weather modeling or materials design, typically you're solving some, partial differential equations using some numerical methods that essentially have typically a quasi-linear relationship between the accuracy of your simulation and the amount of time it takes to run it. In general, and different methods have different order of computational cost versus accuracy. But in general, let's say for the simulation of a car, to make it more accurate, I need to reduce the error in these numerical schemes by having less dissipation, smaller discretization, so these sort of mesh points that you have more of them to be able to capture more of what's really going on. And as you add more of that fidelity in space and time, because most of the time these turbulent structures have a very small, time scale, and particularly true if we start getting into multi-phase and combustion and things like that. The time it takes you, the number of iterations you need to run, and the amount of memory and compute goes up and up and up. So that's why high-performance computing is such an important discussion. It's why I kind of link them together, fluid dynamics, HPC, because they are inherently linked. But the third topic that I mention, I think, in the intro to every podcast is machine learning. And that's why I wanted these next few episodes to really dive in and help. To be honest, me, I learn every time I speak to somebody, but also yourselves to get this sense of why I think machine learning has a strong potential in this area of Formula One and cycling and engineering and fluid dynamics. So what I said before was, in general, all these simulations are getting more and more accurate, but they're also requiring more and more compute. Now, interestingly, machine learning has developed over the past decade, I would argue, but certainly has ramped up in the past 2-3 years to the point that actually, and I'm going to speak at a high level because these next interviews are going to be the chance where we can go in a little bit deeper. So this is, I guess, the sort of 101 class. They've developed to the point that in theory, machine learning is all essentially about inputs and outputs, isn't it? Essentially you've got some input, some data that you can train a machine learning model, some sort of neural network usually, to come up with some weights, etc., that then once it's trained, you can give some new unseen task that it can predict the output for. And to do that, you need some inputs and you need some outputs. So in the context of computational fluid dynamics, the inputs could be lots of cars or planes or wind turbines. It could be their geometries, it could be their volume meshes, it could be a variety of things. But essentially the inputs are usually the simulations of many cars or planes. Or it could be more the same plane or the same car, but lots of different boundary conditions. So different wind speeds, different yaw angles. And the outputs could be their lifts and drags, or it could be their flow fields, the velocities and the pressure at the nodal points on the mesh. And the model is essentially learning that link between those inputs and outputs, such that now, because it's learned that mapping, I can give it an input, let's say a new car or plane, and it can go and predict me that output. But the real reason, I guess, that it's so appealing is because that actual prediction step, that inference step, is essentially nearly real time. Seconds, typically, less than a minute. And if you just focus on that pure inference step, that pure prediction step, and you say it's, let's say, worst case, let's say a minute on what's often a single GPU or even a CPU at this inference step, compared to 48 hours on 1,000 CPU cores, 48 hours to a minute is a dramatic change. And that's why you're seeing many companies, many papers claim 10,000 times faster. And strictly that is true. It's 10,000 times faster, I think, if you do the maths. Now, people will say, rightly so, well, what about the time to train the model? Well, the time to train the model, depending on what methods you're using, and if you look in the literature, is probably still in the hours, maybe maximum a day. So the training cost of time is actually, for these sort of methods, typically not actually that long compared to the cost of a CFD simulation. Now, I'm talking at a very high level here, I appreciate. I'm just trying to set the scene, really. There's nuances and there's different approaches, and that's what we're going to explore over the next few episodes. But in general, the cost of training and the cost of inference is actually relatively cheap. The big one, of course, is you have to have the training data. And this is the interesting similarities and differences between machine learning for scientific problems and machine learning for, I'm not sure how you would phrase it, but for large language models, for the stuff that what you use in these ChatGPT or Titan or Bard or Llama model. In those scenarios, the training data is widely available because it's, and maybe it's getting harder now, but previously it was simply scraping off the internet lots and lots of text and documents, etc. Now many of these companies have signed deals with magazines or newspapers or various other entities to get the data. But I would say it's largely available and not huge in size. So if you look at these models, the actual data itself is, gigabytes or terabytes. It's not in the petabytes. And the real cost of training these large language models that many of you are starting to use is not the data collection per se, although there is work to do the labeling and pre-processing, but more the actual training time. So you might need 4,000 or 10,000 GPUs running for weeks, and this is what's driven this huge boom in AI chips, because the training time is so massive. If you contrast that with and this is where we jump into so many rabbit holes, so you bear with me. For many people at the moment, the big difference is that for scientific problems, many people are not talking about foundational models, and I'll explain what I believe that stands for in a moment, but more that you are training a model each time, essentially. So the training time is for your specific 50 cars or 100 cars or your specific Earth model or your specific drug discovery. And so the training time is actually not that much and not that expensive. What is the real challenge is collecting the training data. Foundational models, the whole point of a foundational model is it's meant to be so foundational that you should train it once, essentially, and then you can just use it. With the exception being that maybe you need to fine-tune it. But when you go and use any of these commercially available large language models, you are only doing a prediction step. You are not training the model. It has already been trained on so much data that is considered almost foundational. There is a current debate in the scientific community, but I think it's fair to say that most of the stuff that's been done to date in the scientific side, whether it's weather modeling or CFD, are not foundational models, because they only work for quite a specific use case that it has been trained for. So it's not able to predict any fluid dynamics or any weather scenario. It is still within the confines of a particular thing. Now, one of the debates is, could we build foundational models for science? And that's one of the topics I'll be discussing with some of my guests. And I'm purposely not saying the names of the on the guest here to keep it. I'll sort of leak that information once they're actually recorded. But it's quite exciting, and I'm really pleased who I've managed to convince to have a chat and share their wisdom. So all of that was to essentially say, why is it so interesting? It's interesting because ultimately the promise is that you can get a method that once trained can run in quasi real time. So if you are a car manufacturer or a plane manufacturer or wind turbine, you can design and explore thousands of designs in minutes. Now that all sounds too good to be true, doesn't it? Well, the truth is that at the moment there is still a active debate on how accurate are these methods and what can they actually do. So there's been lots of, I would say, fundamental work, and there are various startups in the space who are claiming they can do more, but it's a very active area of research that I would say is nowhere near as mature as some of these large language models that people are using every day, and you can actually see their usefulness. But there's a huge amount of promise, and so what I want to do over the next few episodes is tease in where these industry experts think we're at and where we could go to. One of the things that you're probably thinking and I just want to briefly explain and mention, as a context to these upcoming ones, is physics. When you're training these large language models, one of the interesting thing is that when you ask it a question, you ask it to write a sentence, you have not told it explicitly what are the laws of the English language. If we're talking about English now, you haven't told it this is specifically the alphabet, these are the rules, these are the grammar rules. Instead, it's actually learned it essentially from the data. When it comes to, let's say, fluid dynamics, there is one argument that, and this is typically called sort of data-driven approaches, that if you give it enough data, it inherently learns the laws of physics through the data that it ingests, similar to how a large language model is able to essentially learn the language without explicitly knowing the rules. And you could argue this is a little bit how a child learns. At the beginning, they're speaking the language through sort of just observation, through trial and error, without explicitly knowing the rules. Whereas an adult, maybe then you actually have to learn the rules. And that's a whole other topic, how the brain works. And anyone who learns a foreign language knows it's much harder when you're older to do it when you're younger. But when it comes to fluid dynamics, there is the opposite viewpoint, which is that, no, we must include somehow these physical laws in the machine learning model, in the loss function, some mechanism to force it to abide by these foundational physical laws, conservation of mass, conservation of energy, that we know are real and help us. And that is typically what are called more physics-driven or physics-informed approaches. And it's very interesting debate, I would say still a very ongoing debate in the literature, on which one of these is essentially the winner, which is the most correct, or is it somehow something in the middle, where it's a little bit of data, a little bit of physics. This, in my mind, is very interesting, and it's still not clear whether it'll be one of these sort of models that have been coming out, or is it going to be something completely different. So I hope that I've maybe just framed a little bit of what's coming. What really I want to tease out in the next few months is to hear from these people, first of all, where they see the current state of the art, where things are going, and their optimism to what a future will look like in 5 to 10 years. Will we ever be able to have these foundational models of science where we could essentially almost ask it in a prompt-like fashion, solve these equations, and it can go off and do it, just as I can tell it now, write me a script that does this? Is it theoretically possible that if it could learn it, that we could actually be solving some of these fantastic problems just in a few types of a keyboard? It's, for me, it's a super fascinating one, and I know it divides many people. Some people see machine learning as just a huge hype that is marketing. I felt that way a little bit at the beginning. Now I'm convinced actually that there are huge potential changes, and something that everybody should be far more aware of, because I think it has a potentially transformative effect, particularly in the engineering industry, that just as computers and simulation transformed the sector from the previous days of sort of trial and error of physically making things, the question is, how much can machine learning bring out a new revolution in those industries? So yeah, that's this episode. We're going to keep it sweet, going to keep it short, and please watch out, please subscribe, please look out at the next few interesting episodes. I think you're going to like, I think you're going to learn a lot from, and I hope you'll join me for those. So thanks very much for listening to this, and hopefully you'll join us for the next few ones too.